All right. And on that note, let me talk about single-page applications. Oh, also, if randomly I end up talking to a wall or something that seems a little odd, I have enough cold medicine in me to stun a whale. So hopefully we're going to make it through this okay, and that I've correctly balanced all the stimulants and depressants. So the single-page apps and memory problems are something that's quite interesting, to me, at least, and hopefully to you in a bit here. It's actually not very hard to use the tools inside of Chrome, which we're going to take a look at, to figure out how to debug memory problems. The really, really tricky part is understanding what any of the data they will throw at you means. There is tons and tons of data coming out of these things, but you need a framework by which you can interpret the data that's coming at you. So part of what we're going to do, and I will try not to be too slide heavy on this because I want to get to code as well, but we're going to talk a little bit about what's happening inside of modern JavaScript browsers and memory, how things are modeled, what's actually happening internally, the relationship of memory and how things are moving around. I'm happy to take time on that if people have questions, but I'm also happy to just kind of move it through it to get the background. So we'll see how that goes. But that background's going to be imperative because when we get to the point,
push the button. It's okay.
Which button? This one?
Yep. Just press it down first.
But good.
Perfect.
All right, I pushed the button successfully. I know, my first big task of the night done. But when we get to these things, we're going to have all sorts of things like dominators and GC roots thrown at us, and this is how Chrome and other memory debugging tools are going to talk to us, and they're going to provide us, paths to root and distances. And if we don't understand what any of that means, all the great data in the world is completely useless. Hey, Tom, is completely useless without that additional information. So.
He just came so you could make fun of him, right?
No, that's Kyle that I make fun of.
Oh, sorry, yes.
So and I told Kyle I wouldn't do that anymore. Instead, I'd use a pseudonym, Lyle. So, in any case, so we're going to talk a lot about how these pieces fit together because in understanding that, we can understand what the interpretation is. All right? Good? So what we're going to do, understand memory management tools, and then kind of some intuition and techniques along with it. But first, let's talk about GC and garbage collection, just to make sure. Because ultimately, the whole point of these memory management tools is that we are trying to interpret and understand what the garbage collector is doing for us, okay? Everything else inside of memory management, inside of a modern sort of browser-based application is meaningless because we don't really allocate and deallocate our own memory. We ask for objects and we ask for this garbage collector to do the rest of the work for us. So you can think about these memory profiling tools at the end is our relationship that we're building with the garbage collector and how we understand when it is able to do work for us. So the way I like to talk about it is at least from the back end first of where we wish to be. Memory management is a difficult thing. It's much more difficult as applications grow. People suck at cleaning up after themselves. All right, and GC and garbage collection in general is basically trying to take that responsibility away from you, and it's great because it wants you to focus on developing larger applications without thinking about these things. But like any system with rules, if you don't play by the rules, it can't do what it's supposed to do. Now, what are we trying to avoid? In the world before garbage collection, we had a bunch of different cases that normally happen. In the simplest case, we went and had a bunch of memory and we have a couple of different pointers to it and we free it and crap, suddenly we have a scenario where we have a reference to something that no longer exists out in the world. We can also have the scenario where we allocate some memory and we double free it. By the way, for those of you who've never worked in a language like this, although I didn't put the appropriate terms, basically the normal standard way of working in these types of languages was that you said to the operating system, if there was one, if not lower level than that, I want a chunk of memory. And you were given a contiguous block of memory and it was yours to do what you wanted with it. If you didn't free it though, it stayed around forever. Sometimes, depending on the operating system, literally forever. There's nothing that would free it, it was yours, okay? This isn't how we work anymore because people suck at cleaning up after themselves and this is how we have terrible, terrible applications that do it. So most modern languages are garbage collected in some capacity. Now, the word memory leak is thrown around a lot, but real memory leaks, what really actually happens in a system is when I allocate 2 chunks of memory, but I lose access to one of them. So if you can imagine, if I, you hear about it in all of days in modern crypto where somebody loses a key to the cryptocurrency, okay, and it's lost and gone forever. I like to take that as an analogy, but the reality is, if I ask for 2 chunks of memory and I don't know where I put one of them, it's gone, it's lost. I have no way to find it ever again. And that is a reality of real memory leaks in other systems. That's what's actually happening, is I've got memory that I can never get back to. Now, we do GC instead because we don't have to deal with any of those situations, all right? We don't have to worry about finding and keeping track of memory. And to some degree, it's impossible. That's a little bit of an overstatement, but stick with me. In modern web applications, we're building objects and objects and objects, and it's going all the way down, and we get some new data in from a service, and we get some JSON, which allocated a big string, and then we parse it, which turned it into some objects, and then we give a little piece of each of these objects to some different component, and we distribute it out through the entire system. If we had to manually go back to the point where that first came in and say, oh, I'm done with all of these pieces now, I'm able to free up this string, we would never, ever free up anything. It'd be toast. We'd never be able to get there. So the complexity of these applications and the interwoven way in which they distribute data makes it all but impossible to actually manually control data. So we have to rely on garbage collection. The thing is, garbage collection is effectively a set of heuristics. It is, in effect, a best guess at what you're using and what you're not so that it can clean up after you. But it's a guess. So we can do things that make it a lot better and it can guess more effectively, or we can make it absolutely impossible for it to ever guess accurately. We like to say, damn it, there's a memory leak and the garbage collector didn't do its job, when we made it absolutely impossible for it to ever guess what we wanted to do correctly. Okay, those are synonyms for each other. All right, so GC is going to be slower, it's going to be more complicated, a lot more complicated. There's a ton of things going on in there. How? All right. Let's talk about this. This is actually a lot of fun for me, so I promise I'll go quick unless somebody stops me. Like, this is the kind of stuff that I just keep going on.
10:30.
Yeah, well, just keep flag me down, man. Flag me down. All right. So we have two types of memory we're mostly going to care about when we talk about garbage collection. Okay, stack and heap memory. Stack and heap memory are the two types that are in basically every programming language, but they're going to be particularly relevant for us. Up first, stacks. When we're building any sort of memory in an application, our first data structure that we come across that we use, whether we understand it or not, is a stack. Simply put, for those of you who may not be data structure nerds, stacks are the ability to stack things like a pile of papers on your desk where you have item 1 and item 2, and if and when you add another item, it always goes on the top. The only way that you can get an item off is to take one off the top. And the only place you can put one back on is to put it back on top. So, in the case of altering a stack and pulling off item 3 and putting on item 4, I pull off item 3, my stack looks like this. I put on item 4, my stack looks like this. Now you may say that sounds completely reasonable and okay, why do I care? Come on in, there's room. I can start over, but everyone else.
Don't worry about it.
He's not starting over!
I said I
You
could.
could threaten that at 8 o'clock, can't you?
Like, well, let's recover this. All right, so local variables. Every single time you've ever declared a variable inside of JavaScript or any other language, any other higher level language, you've probably used stack space. If I have a function, which I like mixing my ES5 and 6 syntax here for the hell of it, but if I go A, B, and C, 3 lets, I'm actually getting A, B, and C as 3 positions on a stack. Okay, so every local variable that you declare is a stack variable. Okay? Now, interestingly, and this is going to mess with you a bit, but maybe it'll make sense by the end, all these variables are the only predictable part of the entire application. When you actually build an application, the only place that we actually know how much or where something is ever going to live or how much space it's going to take are these variables that actually sit here. Nothing else, everything else is up for grabs after that. Okay? We actually know about those. So whenever we declare variables, we push them on the stack. In fact, stacks are really, really important because when we do things like function calls, the way we can keep track of things in the von Neumann machine that we use is by having stacked variables A, B, and C pushed on, and when we call a function call, the next thing from the next function call goes on a stack too. This is, by the way, why recursion works, because the fact that if we were to start again with do thing, we would just keep pushing more stuff on the stack, so it's okay. We can understand where we came from, how it works, why. Technically, there's one more piece in there, which is every time we call a function call, we not only put A, B, and C on the stack, but we put a little pointer. I like to think of it as a breadcrumb that tells us where to come back to. So when we go to X, we know that when we were done with X, we would come back to here and continue on. So our stack's really, really important, and it's doing this all the time in your application. In fact, this is what happens when I go on tangents. You could think of different types of programming having different shapes. Maybe a little weird. However, if you feel like reading Abelson's Structure and Interpretation of Computer Programming Language, he goes on about it extensively. I'll only do this much of it. So recursion, or really deep programs, which you have a function that calls a function, that calls a function, that calls a function, that calls a function, or something recursive, have a shape that looks like this, meaning that the stack gets really, 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 really deep, and then it comes all the way back up, and it goes really, 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 really deep, and it comes all the way back up. More imperative programs, things like for loops, have a stack that's very narrow. It only goes about this far, and then it stays about that. There are advantages and disadvantages of both of them, but the way that the stack looks, you can actually see differences between them. He's trying to get a hold of you. All right, so in terms of any sorts of function calls that we might do, something like do thing here would push A, B, and C on the stack. When it called sum function 1, it would put do thing on. We got to sum function 1, we put in an X. Then when we were done with this, we pop off the X into do thing. Then we call sum function 2, we put do thing back on, we call Y. So our stack's doing this over and over again. Now, none of this memory actually has to do with garbage collection yet, okay? But these are all the things that are moving back and forth. But where it starts mattering is this. Really simple things are what are on the stack. And by simple things, I generally mean we can have base types, we can have primitives, but a lot of what we have are pointers, okay, or references. So whenever we start thinking something that's slightly more complicated, that is the type of thing that's out here in heap memory. And these are the things we really care about. Because even though we talk about our stack doing this up and down, it tends to be comparatively small amounts of memory versus I load this giant file. One of my, which we're not, I don't think, going to get to, but I was trying to tax the profiler earlier for the hell of it, so I was loading a 7 gig JSON file. Turns out that loads a lot of heap memory. So anyway, but the stack would just be one reference, which is just a pointer to that giant glob of heap memory, okay? So heap memory is what we're trying to manage when we talk about this. And if you remember from one of those slides I did before where I said we can lose track of things, that's because we always have to keep a reference to these things that are out here in heap memory that we're talking to. So when you talk about losing track of something, it would mean that we'd lose that bridge. And if we didn't have something minding this for us, that means we'd lose track of any memory that was stuck out here. All right, so that's what we're talking about. When we go through and we do work with this, everything is a combination of stack and heap. So we have the stack growing and moving, and then we have pieces, like in this case, O1 created an object. So syntax for creating an object. Then we happen to call our doIt function and we pass it O1. So then inside here we have this variable O2. Well, there's really only one object A out there. When we talk about JavaScript, we talk about things being passed by reference. It's kind of a lie. It's okay. But object A is basically an object out there, and we have two references to the same thing. They're both pointing to it. All right? This is going to be really, really important later, because at the end of the day, the way that garbage collection ultimately decides if something can go away is if there's no way left to get to it. So if you imagine the idea that in a system I allocate a bunch of memory, but there's absolutely no way ever to get to that memory again, then for all intents and purposes, I could probably get rid of it because you can't use it anymore. Okay? So we're always going to be looking at these references to these. In fact, very, very early systems that did garbage collection did something called reference counting, where they would actually just keep a little pointer to objects out there. And that worked really well, unless I pointed to you and you pointed to him and he pointed to me, and then we had a circular reference and all of us stuck around forever. Problems. All right, so unwinding. When a function returns a stack, we unwind it, that stack keeps going down, but anything that's out here, as long as it still has a reference, stays in memory, okay? And that's what we're trying to get to. So our goal here on understanding all of these things, ultimately, is how does that go away? How does object A ultimately disappear? And that's what we're trying to figure out through all of the tools, because at some point, we're gonna not understand why object A didn't go away, and we wanna understand why. And that comes to the idea of freeing. Okay, so we need to figure out how to do this. How do we do it? As I mentioned, it's by figuring out what we no longer have a reference to. But like all things in the universe, I need to first define some other things before I can explain those things. So let's go on and explain those. Let's start with something called the, technically, weak generational hypothesis. All right, so the weak generational hypothesis is actually fundamental to the way modern garbage collectors and things like JavaScript work. Its premise is pretty simple. I'm going to keep this, I'm going to make it all the way through, no matter how bad this goes. All right, so weak generational hypothesis suggests that most objects die young. if you think about JavaScript, for the most part, you create an object, you might do something with it in a function, and then you exit the function. You might create a variable and then you exit. But you think about what we do, and things tend to be very local, and they tend to be destroyed or created and then destroyed very quickly. Okay? The idea behind this is that we really have sort of a separation. If we create an object and it's done and we create it, it's more likely than not it's going away soon. However, if it stays even a little bit longer, thank you, Mark, you're very sweet. If it stays even a little bit longer, it is likely to stay around a very long time. So if we have something that survives, let's say a function call or the bounding of an existing function or a couple functions, the likelihood goes way, way, way up. But that is something that the system actually needs to have for a very long time. So we can kind of think about things in terms of things that are short-lived and things that are going to become much longer-lived, okay? And this hypothesis governs all modern garbage collectors that work in dynamic languages. It's not always a perfect thing, because again, it's a hypothesis, and there are some cases where it doesn't work as well. But it is how Chrome and most every other browser works. So here's what we have. If we have an object that is created, it's often going to be tossed away, so we're probably going to try to figure out if we can toss it away. And again, if it's not immediately tossed away, we're probably going to exceed that it's going to play a longer role. So when we get to generational garbage collection, what's actually happening is something like this. All the objects that were just created in memory end up living in one area. They're here. And so everything that we're just barely creating sits here, very quickly created, potentially destroyed, goes away. And it takes time, as you can imagine, and we'll talk about what it's doing, but it takes time to go through all this and figure out what should stay and what shouldn't. So we keep the things that just got created in this area we can check a little bit more frequently. And then as things stay around a little while, we start moving it over to this older generational storage. And this older generational storage, we know by this hypothesis, is probably going to stay around longer, so we do still check it, but we check it very infrequently compared to the young stuff. Okay? This is how Chrome is taken, and this is a hypothesis that started, actually they implemented this in, I think, there was a JVM and then Flash Player were I think the first two to try to implement this in actually production environments. But the hypothesis actually turns out, if you look at the statistics on Chrome and V8 Engine particularly, over the last few years, they've actually taken your what's called a GC cycle, which is the time that we do things, from about 300 milliseconds down to about 2 by using this premise of how much time we have to actually spend in garbage collect. All right. Now, disclaimer. There is no specification for how a garbage collector works in JavaScript. You can make a conforming version of JavaScript and have no garbage collector. It just won't run very long before your computer explodes. So this is how V8 works. Almost all the modern JavaScript engines work very similarly. They do have some differences, okay? Which can lead to pain when we're debugging, because there are differences. I'm talking about it from V8's perspective, both because it's most advanced and also because it has the best tools, in my opinion, to be able to work with. So I talk about a lot of this from V8's perspective, but understand that's not as important. Also, the V8 engine is constantly in flux. They have completely revised this garbage collector 11 times in the last 5 years. So what I am telling you right now is very useful for at least a month and a half. And then we will, then I can come back and tell you more. All right, so it's still a good model to understand. Going along with that generational collector, and this is, I also don't have any problem with lying to you. It's simplification. It's very, very difficult to cover all the details and exacting standards. Some people call it simplification, others call it lying. Either way, I'm giving you some of the details. All right, so here we go. We start with the idea of having all these new objects, right? And so these new objects are created very, very frequently, and V8 calls these a nursery. I should say V8, by the way, because although Chrome is an implementation of the V8 engine inside a web browser, the V8 engine is also an implementation of that is what it runs Node and sort of other things as well, and in the future Microsoft's browsers. So as we sit here, this is the nursery. This is where we actually build these very short-lived objects, okay? And what we do constantly is we have something called a scavenger. And these scavengers are just running in the background concurrently. And they're looking through all of the things in the nursery, trying to see if we still have access to them. And if we don't have access to anything in the nursery, or if we do have access to something in the nursery, we eventually move it over to this area called the intermediate stage. All right, so it's an intermediate length environment. So the thing is, only things that actually still have a reference get moved, which means everything else that didn't get moved is gone. It's dead. We can overwrite it. Okay? So we care about moving things over. Now, it turns how it works then is that if in one GC cycle we move something to the intermediate range, and it's working and it's all good, and we get through another GC cycle and those same intermediate objects are still around and viable, then we go ahead and move them over to the old generation. So our gist is nursery to intermediate to old, depending on how many times they survive this process of being gone through and seeing if they're still alive, okay? So we're moving across this way. Now, technically there's some more details here. These things flip-flop and it does things because Chrome also is a compacting memory garbage collector, which means that instead of it being, does anybody remember disk fragmentation, old hard drives?
Of course.
Okay, cool. Not everybody does.
Who here doesn't remember disk fragmentation?
That colorful little logo.
Don't ask
You're
him.
okay.
I was gonna say, every once in a while at the office, I mention a movie, and then I realize a good portion of the people were born well after that. So,
By the way, the objects that get moved
Yep.
are the objects that don't have any reference.
the objects that move are the only ones that do have references.
Okay.
Okay, so it actually does move the ones that have references, and it updates the pointers to them. But in doing so, instead of it having this very sort of fragmented environment like a disk that needs to be defragmented, since it can just move the ones that do have references, it can always compact them as it moves them up so that they're in nice, clean little areas, okay? And then that way, everything that was left here should just be overwritten because it doesn't need any of it. So it can always keep things nice and compact. And it sort of flip-flops these every time it moves them. It does the same process where it moves them to a more compact space and decompacts those. It also does some other stuff where it keeps some free reference tables to understand what spaces in the old generation it can actually move things to and what's contiguous and all these sorts of things. All implementation details at the end of the day, though. The trick, though, is how the heck do we figure out what needs to be tossed away and what can actually stay? And you all asked, I heard it. So we're going to talk about that.
Please. Thank you.
Actually, just out of curiosity,
Yeah.
I know you mentioned obviously Chrome's turning over changes at an insanely high frequency, but what you're going to show us, how much of that is very specifically applicable to the V8 engine versus going out to the other browsers, even though?
Great question, which is how much of this is applicable just to V8, how much is the rest? 95% is totally applicable across the board.
Okay.
5% of this is specific to V8, all the concepts are the same.
Okay.
Okay? So individual pieces like the fact that it compacts memory and it has 2 pages that flip back and forth, Chrome implementation, the fact that it does something like this is pretty standard. Okay? All right. So since you all asked, we're going to talk about roots, GC roots specifically. So in
Hoping we're going to talk about GC.
I am so glad I was here to fulfill that need for you, Joe. It's kind of what I set out for this morning. Sir?
On the previous slide, how fast was the time frame it goes from each column to the next column?
Good question, which is how fast is the time frame it goes between here? Oh boy. All right, so.
No!
Let's talk about the difference between concurrent, parallel, and interwoven. All right, hold on. A little leg stretching. All right, we're good to go. So, parallel and concurrent are often used the same, but they're not, okay? Parallel is the idea that I can do lots of things at once, but usually it means that we take a time and we say what we call stop the world time, which is we aren't going to do anything else, but maybe we'll have 7 processes that all work together to get it done as fast as possible, okay? Concurrency is theoretically the idea that we don't stop the main thing we're doing, but we do some stuff off in the background, okay? This part is done concurrently, meaning that it's less about time because it's almost constantly happened concurrently. Now, specifically though, it really aggressively does that at the point at which time where it needs more memory. Meaning that if it allocated or if it asked for, a couple hundred meg from your operating system and it's only using 5, it doesn't even really bother to do this very much. But if it gets to the point where it's about to have to ask for more, then it increases the aggressiveness at which it does this so it doesn't have to. So ideally, it always does its best to not have to ask for more memory from the operating system until it gets to a point that it can't help it, okay? But these happen concurrently, and then when we get to the point where we actually have to do this, that's what's called stop the world portion of time, where we actually stop rendering and responding in JavaScript for a few milliseconds. And at that period of time, then with all these worker threads in parallel, it does as much as it can to quickly move everything all around and then resume. So concurrent and then parallel, okay? But total time in a pretty big GC cycle nowadays will be about 4 or 5 millisecond pause here. And again, these are happening concurrently, so while it may happen over 10 milliseconds, we don't notice any performance degradation because of it. Okay? All right, that wasn't so bad now, was it? All right, so.
That was really interesting.
Well, thank you.
I'm shocked.
Kind of one. Well, now I'm going to get back to GC roots because that's what Joe really came here to talk about.
That sounds boring.
All right. So GC roots have a technical thing. I will call them the first chunk of managed memory asked for from an unmanaged memory. However, realistically, what I really mean in this case is it's the starting point. If we think about JavaScript, if we're talking about something like Chrome, for the most part, we can kind of think about window as one of our main roots, right? Like if you declare a function, probably at some point it got declared on something like window, or you loaded a module from something that started at window, or. But we can kind of think about window as one of the GC roots. There are others too. There are some that are related to render frames. There are some that are related to the DOM. But they're these very, very top level things. Now these roots are exceptionally important because if you had to follow a trail figuring out what was used or wasn't, one of the easiest ways to start is at the beginning, right? And figure out where things are at. So in a memory model, we ask for these objects to be managed in a garbage collection scenario for us. So what actually happens is this. We walk. If off of the window, object A was allocated, which then has these objects underneath it, which have these objects underneath it, and these objects underneath it, in effect, a mark is the idea that you take one of these objects and you walk that tree, and you figure out which objects can be reached. Because again, the premise being, if you can't reach an object, then it really doesn't matter if it's there, right? If you can no longer perceive it, if you can't touch it, if you can't do anything with it, it doesn't matter if it's there, it can go away. But if I can somehow get to it, then I need to have it around because that could mean that somebody wants it later. I can't know. Here, we actually have objects that reference each other, but if you notice, they're not connected to the root anymore. So that might be, two objects, two DOM elements, one that's a parent-child relationship, but they're not connected to anything else anymore, so they can go away. Okay? So only things connected to the root are there. And so the process that it actually does when it does so is it walks this root and it marks things. And traditional garbage collectors are called mark and sweep systems. This has something very similar to it, okay? And I guess that's not even fair to call this traditional because that was like new 10 years ago, but now it's traditional. So I'm too old for this. So mark and sweep systems, we walk down this scenario, and as we go through each one of these objects, everything we can reach, we mark. Everything we can't doesn't get marked because we can't reach it, right? And so as we were talking about before, what ends up happening then is that the things that were actually marked get moved. They end up somewhere new. And they end up in this new page. And because we don't want things to crash horribly and fiery wrecks, any pointers to these things get updated. So if there was a variable somewhere else on the stack, as we showed you before, that was pointing to object A basically leaves a forwarding address, meaning that when we move it, we kind of know how to find it again, but it gets moved. And anything that was not moved is, for all intents and purposes, dead. We can overwrite it. That's not actually going in and removing it, it's just overwriting it. Next one, it's gone, right? It's out of here. Okay, so we mark things. As soon as we mark them, we actually go through and we move the things that were marked. Hey, tangent alert. So the
Slide.
yeah, neat, huh? It's very meta. Anybody heard of weak maps, ES6 concept? Okay, a couple of you. Weak maps are a super important, hugely powerful thing as we get into single-page applications because traditional JavaScript didn't have weak structures, which is incredibly painful for things as they grow. Weak maps basically purport, if you read them, to be about containing weak references to things, and those aren't very well understood by most people. So we're going to talk about them for a moment. But it fits in really nicely here, which is the reason that my tangent comes about. Weak references are basically dotted lines, okay? It means that this object can have a reference to this one, but for the purpose of the garbage collector is not allowed to go down that path. It can't follow it when it's marking it, okay? So that means that if the only reference, if the only way to get to this object in this system was from here, then it's going to be cleaned up. It's gone, okay? Now, if this thing also referenced it, it would stay around, but the garbage collector is just not allowed to follow this path, all right? Weak references are extremely important because there are times, like let's say we wanted to have a list of a bunch of DOM elements, and while those DOM elements are out there, we wanted to loop through them and we want to check in on them every once in a while. If somebody removes one from the screen, we don't want to be the reason that it stays around forever. So that's a great example of someplace that we'd use a weak reference. We want to have a reference to that thing so long as we're not the only people that need it. Okay? If we're the only people that need it, it should be allowed to go away. That's what a weak reference is about, and this is how it's implemented. All right? Okay, I'm off my tangent. Look at this. Yay! Back on track. All right, so all that said, this stuff's easy. Because basically, we really only have two problems that actually end up happening inside of systems. Now, granted, they're two large categories of problems, but we only have two. Are we using too much memory, or are we leaking memory? Okay, and they're different. Too much memory means that the system is using more memory than we think, but it doesn't necessarily mean it's growing at a weird rate. It's just using more memory than we'd like it to. Okay, so it might be slow, might be bad, it's not great, but it's not growing immeasurably, right? This is extremely easy to identify. We can find these problems right away. Just ends up being super hard to fix. Okay? Here, we have the other side, which is leaking memory. If we leak memory, it means that the more we use the system, we continue to grow and we don't know why. Performance just keeps getting worse a little bit at a time, maybe very slowly, maybe quickly. Now here's the fun thing. These are really hard to find. However, then usually you end up fixing one line of code and it's all better. But it just takes like a week to find that one line of code. Okay? So you have two very, very different problems in terms of what you're actually doing. Make sense? All right, let's look at some code. We'll actually do...
I'm a little old. Can you zoom in?
I am getting there.
We just loaded the
My God, people.
Too
big! There we go.
Professional.
Now there's no complaining. All right. Let me just load my complaints.json.
It's just got Mark and Joe.
Yeah. So, we'll start here. All right. So, we've got a really simple page, and hopefully this will be exceptionally simple to work with. This is index 1, some refs. All of the pages are going to look exactly like this. Some of them I even remember to change the title on. Not all of them, but some of them. They all have a button because we don't need to do a lot more than that to illustrate things, although we will talk briefly about some React things and other parts later. Here's the thing. Everything I'm going to show you applies regardless of the size of the system, but the number of data points goes up. So if you can imagine, if each one of you is tracking 2 other people in the room, it's a lot harder when there's 10 people in the room or 100 people than if there's 2. So the point of showing these simple examples is that they're the same thing, but it can get very easy to get lost in the complexity when you start off with lots and lots and lots of data points. So we're starting a little smaller first, just to work our way up, okay? So I promise you the principles are the same. We're gonna go in and we're gonna open the couple different tools. Actually, there's a couple of different ones that are interesting here, so let me show them to you both first. The really most crude version of something that is useful under more tools here is there's this task manager that you can actually use in Chrome. So under more tools in task manager, it's crude, okay? But in a pinch, it'll get you by, so keep this in mind because it actually will save you sometimes. Or maybe you don't want to open. There it is. Oh, when you have multiple monitors, sometimes weird things happen. Or, I don't know why that's happening, so give me a second. It says it's open, I just don't know where. You can see it's there.
What is it?
It's opened on a mystery screen that I don't have. Let's try and open that again and see if it'll readjust itself. If not, we're just going to skip that tool and go on to the next one. There's only so much you can do. All right, let's try this.
Okay, do Alt, do focus on that window.
Yes.
Human meat, Alt
Yeah.
space,
Alt space.
and then move it with your cursor.
That is a great idea.
Oh my God, look at that.
What? Look at what?
Space,
Yeah.
move,
Move. Do that.
cursor right.
Yeah.
Oh! I have purpose.
Windows guy.
I hate multiple
All right.
monitors too.
No, it's fantastic. All right, so in this window, you can turn on lots of different things, okay? And this is very crude. It's a very crude tool, but it is a useful tool if you understand its purpose, okay? If you right-click in here, these are all the different things you can turn on. They're really basic, simple like concepts. Right now I have JavaScript memory on, okay? So these are going to show you really basic how much CPU time, how much memory any one tab or piece inside of a window is opening. It's not going to give you details, but if you're really looking just to find out, is my memory growing over time? What am I really using? You can do this in 3 seconds instead of all the other tools that I'm going to show you, which take 20 minutes, right? So there's a purpose for the 3-second tool, even if it takes a minute and a half to get it on the screen. All right, so there's the, I just wanted to show this. Now, I am going to do everything else in an incognito window. Any idea why? That was my first guess as well. However, what was the other answer?
Extensions.
Extensions and everything else, because every extension you have is technically written in JavaScript, and all of them eat memory. All of them use pieces and processor time and allocate things and deallocate things. And if you're sitting there trying to profile something and you can't figure out what is allocating memory, and then you find out it turns out it's last pass, it, kind of aggravates the hell out of you. So we're going to do everything in incognito just to limit that, all right? And to limit the number of times that we're going to get interrupted by things that are sort of false data points. So to that end, let's do that, right? Now, in here, once we have this open, everything else we're going to do is going to be by bringing up the Chrome developer tools, which I should be able to increase in size a bit too. All right, we are specifically going to hang out on 2 tabs tonight, the Performance tab and the Memory tab. The Performance tab and the Memory tab are both very useful for sort of different glimpses of things and different aspects of what we want to understand from memory. The Memory tab is infinitely more detailed, okay? But it's also harder to interpret everything that's going on. So you got trade-offs, right? This little checkbox right up there that's hiding at the top happens to be the most important one if we're going to use the Performance tab. Because what it really says is it tells it to decorate the Performance tab with information about memory, about what's actually going on in allocations. Was there a question?
No,
No.
just
No problem. Yeah, just making sure. The Memory tab.
that guy's new.
I'm here all night.
Welcome to the
So, profiling. There's 3 types of profiling. We're going to go through at least a couple of them in the course of tonight. But basically, you can think of these types of profiling as either a heap, the first one being a heap snapshot, which is the idea of just a point in time. I take a snapshot right now, and then I can compare it and do things with it to snapshots I take later, but they're very static. They're also a lot more performant and quicker to use. And then we can do really cool stuff with this allocation instrument on timeline, but it's really, really slow because it's trying to gather so much information that all of the execution of everything you're doing is slowing down by like 300%. Okay? So we're going to use all of these tools at least in some capacity. Let's go look at this amazing JavaScript application that I put together for all of us tonight. It's right here. This application basically adds an event listener to button for click, and it builds this. Now what this is in this case is a single let statement called SumRef. And then SumRef is set to an object that has a foo, bar, bat, and an elements property. And inside the elements, I'm creating a single li, okay? And that's it. I'm doing this because I want to start talking about that whole pathing from GC roots we talked about. And by having these really crazy, stupid names in an li here, it's going to be really easy for us to see what that is. All right? So we're going to go over here, and we are going to take a snapshot of our heap right now. And I'm going to have to make this just small enough so I can get to the buttons. All right, we take a heap snapshot. So this right now is a snapshot of everything that is in memory at this moment. And there's a couple of really important things to understand on this screen. First of all, Shallow size, then retained size, then distance. Shallow size is the amount of memory that that individual element takes up by itself. Okay? The retained size is the amount of memory that that element not only has, but causes to stay in memory. Okay? So if you imagine if I'm an array, I might only have a little bit of memory, but if I'm an array of objects that happen to be, entire web pages by themselves, I'm going to retain a lot more memory, even though the array is actually pretty small. Distance is that graph I was showing you. Remember when I said these are the roots and this is what the tree looks like? Distance is basically how many levels down that tree I am away from a root. Now that's really important because if you're looking for a memory leak, you basically have to trace your way back up that tree in order to figure out why something's staying around. So something that has a distance of 50 requires a lot more coffee than something that has a distance of 2 or 3, okay, when we're going through it. All right, so right now, there's not a lot of memory because of the fact that, quite frankly, this is just, starting up, right? All we've done is rendered this little page, and there is a lot, comparatively, I suppose. Who would have thought you needed, 3 typed arrays in order to render that button? But you do, so that button's on the screen. I'm going to click it now, amazingly. That was an applause. Thank you. All right, now, I can take another snapshot. Now, when I take that snapshot, this is all that information I just had, and we could actually look in here by ourselves for a bunch of stuff, okay? In fact, actually, if we come in here and start looking for HTML elements, we'll actually be able to find some of those things already. But even cooler is that we can take this snapshot and we can say, instead of just a summary, I'd like you to compare it to snapshot 1 for me. And now it'll show me just the things that have changed in between those 2 times. And that's going to narrow down this thing a whole lot. And in fact, it's going to show me this really cool, interesting thing right here, which happens to be a detached HTML element, specifically an LI. And it says that I happen to have one of those in memory right now. And the delta was one of them has been added since the last time I took a snapshot. And then it tells me exactly how much size it's using and things like that. Now that's cool in itself, and it gave me some information to be able to work with. But if I click on this thing and open it up, I start getting a lot of really cool stuff. Because what it's going to tell me down here is that that element itself was contained in index 0 of an array that was in an elements object, that was in a bad object, that was in a bar object, that was in a foo object. So this is basically tracing this back through some ref to a root. What everything this thing is trying to do for me, if you look at distance 9, 8, 7, 6, 5, 4, 3, it is tracing it back to the root. It's trying to tell me what the pathway of this thing was. Because if I don't know why it's hanging out, that's my pathway to figure out how it got here. What's going on? Where did it come from and why is it here? Okay? Now this is very static information. It's very useful, but it's very static. This is showing me how it got here. We can alternatively also see information about when it got here. And that's where the performance tag is actually more useful. In this case, I'm going to leave memory on here, and I'm going to tell it I want a performance snapshot. And I'm going to click this do something, and I'm going to stop again. Now, here's the really cool thing. The performance snapshot is going to tell me and show me things on here about what I'm using in terms of memory, when and where all these allocations happened. And so I can actually narrow down now and figure out things like what happened at this point in time, what was going on, and what objects were created as a result of the event click. And by the way, what function was it that actually created that thing? To the point where I'll eventually be able to find out, there's my function that created that memory that I was looking at. Sir?
Without diving into React or any others, how much of this do you lose when you go into like a React or an Angular?
You don't. It's just more complex to know how to read it.
Okay.
Okay? You can use it all. It's there with one exception. Here's your $1 million free tip for the night. Never, ever, 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 ever,
Use reroute.
ever.
No. That's not what you would say.
God. Ever try to profile a development version of a React or an Angular app. Because as much as it's more useful to see the code that way, they actually do all sorts of things inside the development version to try and make it easier for you and cause tons of memory leaks. Your React development app will use 10 times as much data and keep most of it that a production version won't. So when it comes down to memory profiling, it's different than debugging. You really want to do this on something that's as final form as possible. The number of hours of my life I've spent debugging something, which turned out just to be because of development mode of some library, is embarrassingly large. All right, so here we are to the button where we actually created something. That's pretty cool. We can see something that actually goes on. So let's look at another example here, because at some point Dave's going to, Mark's going to stop talking. So let's go to many refs. Now, many refs is a very, very similar application to the last one that we had. The difference is I've taken this large refactoring opportunity and put SumArray up here, and I've put this thing in SumArray first, and then I've embedded SumArray in here. Okay? Simple change, but it's interesting to see what's going to happen over here. So as I come into the memory application and I come down to many references, let's clean this up so that we can get rid of the stuff we need. All of these have various sorts of clear. Snapshots can be cleared. You can also keep them around, by the way, between applications and different versions, which is pretty neat, because you can have an A/B. You don't have to lose your data, so you can have like A version with a bunch of changes in it, get the memory from it, go make a change to the code, run B version, and see what the differences are. It's very useful, but sometimes when you get like 20 memory snapshots, since they're all just named poorly, it gets really hard to figure out what's going on. All right.
Export that stuff?
What was that?
You know
You
if you
can. You
never
so
tried.
can. And you can load it back up later.
Oh.
All right.
Export and import.
Don't ask him how.
I can't ask questions. I
Don't ask him how, no.
You are a mean person. All right, so I'm going to click again, do something, and I'm going to take a memory snapshot. When I take a memory snapshot, this time instead of doing the comparison just to simplify things and make sure I don't get in trouble, I'm going to go ahead and look for detached HTML elements, which is that one that we saw anyway. So I just filtered it down, right? And when I filter this down, I can look and I can again see that element, but I'm going to see something slightly different this time, and it's going to be important. You'll see that now I actually don't have one, but I've got two routes that are keeping me in memory. In other words, there are two different pathways that are going to keep me in memory, one of which has a distance of 8 and one of which has a distance of 4. So as I go through, I can, as a human, figure out that's probably the one that's 4 that's a bigger issue for us. But if I look through, I know I'm right on this array that's right off of the GC, or again, if I go to this one, I'll see that I'm in bat, bar, foo, sumref. Okay? So in practice, most of your objects are going to have more than one pathway back that are stuck in memory for some reason. But it's important to understand here that that's what we're actually seeing, is that we have multiple pathways back from two different approaches, two different distances, and potentially two different sizes in terms of what's retained. Okay? Does that make sense, everybody?
What is the sizes difference? Is it?
One has the whole object structure of the bar
Oh,
back.
it's the retained size.
Exactly. Okay?
Oh, so it's up?
What was
It's
that?
retained size.
Well, I'm holding on to the one reference, which, yeah, it's entirely, they're interrelated at that point. Okay, so let me go on to this other one real quick for us, which is the amazing one called string growth. Now, I'm very proud of this one.
Is it string growth?
String growth.
Fedcrimes.json.
Yep.
Okay.
You gotta keep track. I mean,
Well, the complaints one was very small. It just had you doing it. So I needed something a little larger as far as the data set. It's funny how slowly 8 gig JSON files load. So, all right. So this one's called lots of data. It takes a string called long string. And every time I click the button, it adds to that long string an array of 5 of those long strings. So it's exponential growth based on the string length as it goes along, okay? And that exponential growth is going to make it a whole lot easier for us to see. Now what you're going to see in a moment is something I'm going to do, but here's another little tip that goes along with it. You'll see me click this, this button a bunch of times and we're going to look at the data. But when you're doing memory profiling and any sorts of these things, there's this law of prime numbers, which is pretty cool. If you do things a prime number a number of times, let's say 7, not larger prime numbers, then you can actually pay attention to which other objects are in memory, multiples of 7, because they may very well be related to the thing that you're doing. So it's kind of a neat trick to actually keep track of like what things might be affected by what you're doing at the moment. So kind of a trick I've used many times successfully, and lots of times unsuccessfully, but many times successfully. All right, so lots of data. Let us go and we'll start over here in performance profiling land. And we'll take a performance profile. And I'm going to click do something and do something and do something again and do something again. And we'll take a look at what our memory looks like here. And you'll see that if I were to keep going, we're going to continue to step up. And we can, in fact, see up here as well that our memory is growing. Now, as I mentioned earlier, and this shows a really cool piece, on startup, we allocated a certain amount of memory, and we probably didn't need it all after the initial build was done. So the very first time I went to allocate some more string, it said, oh, I'm about to get memory from the operating system again. Oh, let me collect what I have first. And it actually dropped down. And then after it dropped down, then we're slowly building it back up. And of course, because I made an exponential growth pattern, we'll continue to grow in that way. But going back to what I was mentioning before, I can come into any of these areas here, and I can zoom in on them. I can theoretically zoom in on them. And in doing so, I can actually narrow down what the cause of that particular piece was and why I actually did it. So again, I'll end up seeing a mouse up, and if I dig down into here, I'll eventually be able to get to my function that actually caused it to happen. Make sense?
When you go to do that, what are you looking for? Like, if you were actually realistically blocking out sections of time and what happened, like, what would you be like? Oh, is it 3 seconds and that's it, or is there more to it?
No, in this case, I'm really trying to capture that edge, right? So I care about the edge. But all of these things, and you can turn more and more things on here. We didn't dive into them, but you can see when things render, when GPU is active. You can see a whole bunch of different pieces. So it's really going to be very dependent on what your application is doing. But in my case, I'm seeing, wow, there's geometric growth. So what I would actually do if I was going to debug this is I'd be looking for every one of these edges and comparing each one of them and seeing which functions happen in the same edges. And that would be my starting point for doing it. Okay?
Hey, Mike. Can you go back to right where you showed where the GC like dropped off did a bunch of collecting right there?
Yeah, right back here.
Because you said, well, there was like a little hiccup right before.
Oh yeah, yeah. The hiccup that went up first.
Yeah.
Because what actually
you don't
happened?
have to have it there, but
Yeah.
my question is,
Why?
Is that the incoming memory?
Yeah, that was probably right up to the maximum it had. So that was, oh, I needed some memory, and it got right up to the maximum of what it had, and then went, I'm going to have to ask for more from the operating system.
Okay.
And so that meant it did a GC, and then it reclaimed everything it could, and then it reused it, and didn't until later actually need to go back to the operating system again.
So, but that little hiccup right there, that little bump right there, is
Yep.
really referencing like, oh, now there's new information coming in. I'm going to go ahead and clear out old stuff.
Yeah, well, it was the start of it trying to do what we asked it to
Yes.
do, and then it realizing it was time to clear out some old stuff first.
Good.
Got it? And so you'll always see that all of these garbage collectors are what's called allocation-based GCs, which means they only really attempt to clean up things at the time when somebody might want more. So it's really unlikely unless you'll see some of these screens actually have a GC button on them. You can do that from these tools. You can put the little garbage can in, it'll go in and try and garbage collect for you. But there's no way to do that in JavaScript normally. Okay, you can't ask the GC to run. So we're never going to actually generally see a drop unless it was because somebody asked for more.
Can you trick it into doing that by allocating?
You could try to allocate as an effort to do so, yes. It's probably a bit of a dangerous game.
Yeah,
like things are running really slow. Let me ask it for more memory. I suppose with the right heuristic, anything's possible. All right.
I feel like that is a strategy.
It is.
I remember that for something like
All right, so let's go over here and we're going to do the same one, which is a timeline view over here now. It's the first time I'm going to do this one. So I'm reloading this to restart my growth, and I'm going to tell it to record allocations. And there's a little bit of a trick here, which is that I am going to try to be careful because of the fact that I can actually very quickly overwhelm what it can actually handle as far as string length goes. All right, so if you saw that little beautiful growth curve there that was going on as it was continuing to bounce up and up and up and up and up, you will very shortly, because of the fact that I'm basically concatenating this to one string, you will get to the point where it's like, no, you cannot have a string this long. I am not letting you. But for right now, I can do this. So these retain size and shallow size are really helpful because I can just sort everything if I wanted to by, hey, what are the biggest things in memory? If I'm really looking for what's causing that giant growth, what are the biggest things in memory? And right now it's like, oh, it could be that ½ gigabyte string. That might be the source of your problem. And if I'm like, you know what, I believe you that could in fact be the source of my problem, and I go into it and open it up, yeah, it's kind of showing me that may in fact have been the source of my problem, and that I went from starting each one of these from each one of these sizes as I grew up and how much memory I was actually taking. I can also see if it'll go, and it might be slow at this point. All right, I might have overwhelmed it a bit, but you can generally see the allocation track too, which is where that actually came from. Now, conversely, I can't see these both at the same time, but they're both really useful. I'm going to clear this just to give it back some memory, and I'm going to go back to the heap snapshot for a moment, and I'll refresh this again. On the heap side of it, I can do 1, 2, 3, 4, 5, and I'll take another one, and if I do the distance between those, this one and this one, come here, oh, wrong button. I will again see that there was a small delta in strings, and again, I'll be able to see where it came from, and in fact, eventually it will give me enough information to know that that was happening in my map. If I go look, that was where I was actually doing it with my from map. So it's giving me enough information. Thank you. That would actually be great. I'll finish this one up. So if we look here down into where this all came from, it's eventually going to give me a line number that I can work with, which is it's telling me, hey, you idiot, this is where you're allocating in your from map your giant string growth. Okay?
Oh, thank you. Where do you find yourself?
Thank you, Mark.
Hey, Mike, where do you find yourself starting the most? Like, if you're just like, hey, performance is shitty, where, where would you start? If it
So
was from your
I
side?
usually try to tease it apart in those two categories I started with, which is run it and see if its growth is growing over time or growth is flat but just bad. If it's flat but bad, then we look for big structures and see if we're just allocating more than we need or retaining more than we need. If growth is getting worse over time, then that generally means that we're not cleaning things up. And it's those two different things, because at that point you're really separating into two different problems. But I always start with trying to see what the shape of growth is. Is the shape of growth this, or is the shape of growth mostly flat?
I was going to say, do you see more radical jumps or gradual over time as an application goes deeper into whatever the hell it's doing?
Yeah, it's going to depend on what the problem is. But most of the time it's going to be gradual. But you can run these things, especially some of these, over hours-long periods if you need to, and let them go. But for the most part, especially if you get to the idea of where you think there's some problems and do some of the prime number tricks and stuff I talked about, you can usually get pretty quickly down to a rough range where you think the problem is.
And this is totally way far off, but is this something, can you hook this in like automated style stuff? So if you were running some like Selenium stuff and like doing a bunch of like end-to-end type tests, could you hook this in and export like out data?
Trickier because the Selenium driver only pertains to this part. It won't interact with anything on this side.
Got it. Okay.
All right. Okay. So that's how you build a string that'll eventually crash the browser. I think that was the point of tonight's lesson. But you can, in fact, actually eventually crash it. It's right around 0.5 terabyte that it just won't go any further. We thought. All right. Let's look at the same thing. We saw string growth there, but that's a little tricky because it's just one long string, right? It doesn't give us a lot of information. So what if instead we wanted to grow objects? What if we wanted to say, well, every time we have this array and we're going to take everything that's in the array and then we're going to add, I don't know, 5,000 more ULs with 3 LIs underneath it. It seems like the kind of thing you might want to do. So what if we were going to do that? All right, well, that would be interesting, right? Because that would be kind of a cool thing. So let's go take a look at that one. All right, so from here now, let's go in and we'll actually eschew the performance view for right now and we'll stick in the memory view. We'll kill this. So we're going to go ahead and load that up. We're going to say do something, and we'll say do something a few more times. Okay, and then we'll go ahead and take ourselves a memory snapshot. Oh, by the way, you really will know if you screwed up if clicking that memory snapshot button takes like 1.5 minutes. Because one time I may have sort of built a memory leak like that in, where when I clicked that button, it went ahead and counted up to 5 gig. And I kind of knew that maybe something wasn't right. The application was still surprisingly responsive for the 5 gig of RAM I was using. But turns out, all right, so these 65,000 detached UI list elements that I have right now could be something that is maybe part of what's going awry here at the moment. So if I look, I've got a couple things, right? If I look at either shallow or retain size, and they're useful for different pieces. Ultimately, the biggest retain size thing is always going to be window, right? Because window pretty much has everything underneath it. So retain size is more useful once you understand what it is you're looking for. Shallow size tends to be useful to give you a sense of what it is that is probably causing the problem at a deeper level. So in this case, it's pretty clear that it is UI list elements that are actually the problem. Because if I look at all these UI list elements, I will see that, yep, there's a lot of them. In fact, at the moment, at a distance of 6, there's, plus or minus 65,000 of them in memory. And here's where I find them. I find them in this array, in a variable called long array off the system. Additionally, though, which is pretty neat, I can actually also find the LI elements. Okay, because if you remember, I had a parent-child relationship with the LIs being inside the ULs. So I can find the LI elements, of which there's 195,000 of those, because of the kind way that I wrote that code. And when I actually go through, I will see those at distance 7. They're one more step removed, right? And when I go into here, I will actually see, oh, well, that detached LI element, well, that is being held onto by this UL element, which is being held onto by in position 2656 in this array inside of long array right off the bat. Okay? So again, it's tracing through each one of these steps for me. Now, detached UI elements are actually a very large concern, especially in environments. It depends, actually, in different environments. I'm not going to generalize, but UI elements that are detached are UI elements that are no longer on the screen, but are still in memory for some reason. Now, it's pretty common, especially in React, to have some of them floating around, because React does a whole bunch of caching to try to give you back those. So if it gets the sense that you're likely to use them again, it may not get rid of all of them. But over the long haul, they shouldn't grow. Okay, so growth there is then your concern. Make sense?
You're an hour in.
Was it?
An hour.
I got an hour left? That's great.
No, you're an hour in.
I heard an hour left.
Yay. I hope you're halfway through.
You know what? So we are where we are, just so everyone knows. If we want to take 2 minutes, if you need to hit the bathroom.
Yeah, is it? You know what? If you want to do that, and I'll rest my voice for a moment. That'd be great. Is that cool?
Just offer. You don't have to.
You can't launch a conference if you die.
All right. Do that real quick, and then we'll resume in a moment. As far as the other one, it's harder, which is the question of what's a bad number as far as just size of the application. And at that point, really realistically, it comes down to, are you seeing a performance problem, or are you targeting a device that could have a performance problem? So case in point, if I'm targeting a mobile app and I can't make my app work in less than half a gig of RAM, I might have a problem, because I'm going to have some form of issue when I get to that device. So I think for the most part, I would start with saying growth is the big concern. And if growth itself is in check, then realistically, you're just being constrained by what sort of device you want to deploy it to. And let's face it, modern desktops are pretty forgiving. They can go really pretty hard on these things. In fact, I'm being honest, that one I was using that was using a 0.5 terabyte of RAM, or no, I wasn't using 0.5 gigabyte of RAM. I did do something the other day, I was using 0.5 terabyte of RAM on my computer, which was really funny, by the way. Not for my computer, it was great. But the
I have a 0.5 terabyte of RAM computer.
well, I don't either. But it turns out, if you override all the settings for the page file in Windows and tell it it can use your entire hard drive, it will keep trying.
Seems realistic.
It did run for several hours before I think it must have overridden the drivers in memory, because then everything crashed really hard in some really cool displays. But anyway, it ran a really long time first. All right, but sustained growth, keeping growth flat, or very minimally upswing is where you want to go to a predictable level. And then device. Am I targeting mobile? Am I targeting desktop? What am I doing? Because even at using a 0.5 gig of memory, which is what I was actually indicating, or trying to, you don't even notice it on a modern desktop. But, in what's actually happening, it's sad, but it's true that it doesn't even get noticed. So I guess device is my other border there. Okay.
Sure. So do you use anything to notify you when it uses too much memory? Like you say, your device is half, right? And a
lot of my users scream at me.
Okay.
So yeah, so you can set up. There are tools out there that will actually allow you to set up alerts and stuff if you're using memory and going over, especially during testing phases. Those can be very helpful. I don't have a lot where I'm monitoring it necessarily, but if you look, it depends on the market you're in, because tools, for instance, New Relic and things like that out in the world for enterprise licenses are great in the sense that they will actually give you real-time memory profiles of what your JavaScript applications are doing in the field. And if you're able to spend the dollars on it and get the reporting, they're fantastic tools, but I don't know that there are many that are particularly accessible outside of a large enterprise environment. Fair?
What do you think of Dynatrace?
What was that?
Dynatrace.
I think there's great stuff. There's really interesting stuff. They've been going back and forth for a long time, and it's kind of funny, actually. But anyway, we can talk about that more later. All right. So statistics was the last one I just wanted to show you in here real quickly, which is sometimes it is just really helpful just to come down to this level of saying, where is my memory at? If we would have done this in the strings one, we would have seen something very different. But I would say on your question of where does things get out of control, if I have 127K of code and 4, meg of arrays already after clicking a button 3 times, I might have a problem. I might have more than one problem. All right, let me hit the other one so that I don't get yelled at by Mark. We will come over here to
You got
index.
15 minutes.
I know I'm doing really well tonight.
Okay, if I tell you have 5 minutes, will you go quicker 5 times?
Yeah.
That math
It'd be
doesn't
3
work out.
times.
No, 5 times. So he's not going to stop at 15 minutes. That's why I'm turning 15 minutes.
All right. This one is inspired by a real example of something that happened, and I just kind of want to show you this one, which I think, and then I want to talk the rest of the time, for as long as I'm allowed, about event listeners. Because event listeners are the single largest cause of all memory leaks inside of every JavaScript application. This is inspired by a real piece of code that I saw. That wasn't this piece of code, but a real piece of code, which is that there was a recommended. We set it to an array that takes 50,000 items and maps it to some LIs, just 50,000 or so at a time. And then it just resets the array to nothing. Okay? So that should be pretty simple, right? We should just see this thing garbage collect over and over again. It should go nowhere. So clearly I made it this example because that's exactly what I'm expecting is going to happen. So we will go ahead and we'll click this a few times. And we'll take a snapshot and we'll say, all right, cool. Well, it looks like we've got a few detached elements there that exist. So why is it that I have 50,000 detached elements? And this is an aside because I have a lot of those, but this is my why you should use strict example. Because I want you to look really carefully at this. Because in one place, somebody spelled recommended with 2 M's, and one time they spelled it with 1. So this is actually a global variable. And this is a local variable that keeps getting reset. And this is a global variable that is now being full of LI elements. I debugged that memory leak not too long ago, so I thought it was worth showing tonight. That's why strict mode exists, so it yells at you when you do that. Okay, cool. Yeah. I
can't spell it.
I'm a terrible. Word has made sure I can't spell anything. It's too easy. All right, event listeners. Event listeners are the single biggest problem for a number of reasons, and they intertwine with some of the weak stuff I was talking about before, but they're let's go with completely misunderstood. Okay? When I add an event listener to an object, I am asking that object to notify me when something happens. So, Joe, you're my event dispatcher, and I don't want you to think it's because you're loud in any way.
All right.
So you're my event dispatcher. If I ask you to notify me when it's time, I'm not asking him because he will. But if I ask you to notify me when it's time, the way you do that in a system is that you keep a reference to me. Okay? Which means, for a moment, that if I'm a lowly object, just over here, and I ask Joe to notify me, Joe promises forevermore to do so, and he will go to great lengths to make sure that can happen, including making sure that I can never leave memory so that he can always do his job forevermore, keeping me around for that one important time in his life when he needs to notify me. I will be there for him.
I feel like
I will be there.
Metaphor for
Federal job.
So, if we look at this for just a moment, I'm skipping my index 6 lots, which is where I pull in the Fed crime data for now. If we look at our little event listener thing here, I think it's actually kind of fun. The code's a little obtuse, but stick with me. There's a reason for it. If I go here and look at this event listener, all I'm doing when the button is clicked is I'm adding a new event listener to the button. And it's to this little function here, which is going to just log out an ID. Okay, so it's going to...
That got a giggle, but that's not improbable. I mean,
It's not a
that
problem.
happens.
Yeah. I set up 2, it's not impossible. So all it's going to do is log out an ID, which it's going to keep in its closure scope so that it can always go on. Right? So this is really cool because it's this tiny little function, and the only reason that it was even created is because I called toID logger right here, right? It's never kept in any other scope. It's never kept around. I don't keep any other references to it in the world. But when I go and do this, and I click this, we can actually even just see this one with the console log. The first time I click it, I will get the 0 from the ID logger. And the next time, I'll get, well, 2 zeros. And then I'm going to get 0, 1, 2. And the next time it's going to be 0, 1. And that's going to get really long pretty soon. Because every one of those little anonymous functions I made in there to log something out is forever and ever and ever and ever and ever and ever more going to be held in memory. While that thing is notified because this thing feels very, very, very much like it needs to notify what's going on, right? So this is held in memory by this anytime we set up an event listener. Does that make sense to everybody? And by the way, with all of our power inside of things like throwing little functions and anonymous functions in React and passing them down to something and refs and all these fun things we do, I only see this every day. So this is the type of thing which is constantly a problem. Go ahead.
So how are reference related, like in Torn, were those diagrams?
Yep. So that's a great question. Let me go to my diagrams. It's great having diagrams. All right. So quite literally, and I can change the name of it in a moment, but if this was button and this was my function, then button will always hold on to my function. Button will be pointing to my function. Okay? Because if you think about it this way, and this is it's not exactly this, but it's very close. Anytime I add an event listener to something, it takes a pointer to the thing I need to notify, and it adds it to a list in my memory space. So that I have my big old list of things that want to be notified when I get clicked. And really an event dispatcher just rolls down that list and calls each one of them and passes it an event object.
That's interesting, because on the tree, I thought like if there is no reference to that one on top, to that object, then it marks, and then
Yep. But
then it's not moving, right? It's
Right.
the garbage collector.
But in this case, the button never went away. The button is on the tree, and now button is pointing to all of these things.
So if there is no reference to the top, it's still going down on the tree to check references existing?
No. If there's no reference on top, it would never get to that tree at all. Okay? But in this case, button is there. This button that I put out here, this one right here, is there forever. I don't remove it. Okay? But what I have done is I've added a whole bunch of functions and asked button to call all of them if it gets clicked. So you can think about it in this way. This right now is button, and then underneath it I have all of these functions that are asking to be notified every time it's clicked. Okay? So if button was removed, all of those would go away and we'd have no problem, because we wouldn't get there. But as long as button is there, all of those have to stay in memory. Does that make sense?
So by creating that function and setting another button, right? So it's growing the button.
Right, because basically button exists,
Yeah.
and what we're really saying is we want our function added to a list inside button of who needs to be notified. But that list is inside button.
When you create that new event.
No,
listener,
it's creating more listeners. There's still just one button, and each time it says add listener, it's like append to a list. So it's appending another callback each time you add listener.
Yeah, hold on. You know what? Give me a second. I'll see if I can write up something that makes sense. Were you going to ask a question?
Yeah, I was just to comment on in our framework, we actually implicitly remove the listener after we're finished with it.
Right. That's the interesting part. The thing was, we remove the listener after we're finished with it. And there's the question. How does one for sure determine when one's finished with something? Because that is what you should do, right? The listener should always be removed. We need to know, though, what it means to be finished. And we need to know when somebody did it on purpose and when they didn't. And that goes back to what I said in the beginning about GC. We really don't have, a lot of times, it can't guess on when we are actually done with something. Really quickly on the button thing, if you imagine this. Imagine that button exists and has a list of, what was that?
10 minutes.
10 minutes.
Yes.
Got it. 10 listeners.
Ish.
So let's pretend I have inside. I have a list of callbacks. Okay. And actually, to be honest, it looks a little more like this. Let's say that we have a map, and we'll have something like click, and here's my list of callbacks. And then I'll have mouse up, and here's my list of callbacks. Okay. Which it's a list, but for right now, we're just going to say that it is. We're going to leave it off as an array, just so we can kind of keep track of it that way. Okay. When I say button dot add event listener click, that literally means I want to be added to this list. Okay? And if I say function all right, and actually let's do it this way just to simplify this first. We'll do it in 2 steps, okay? So let's take this function and leave it out here for a minute, and we'll call this function foo. All right, the moment I execute this line of code, foo is there, right? Foo is put on that list. Now, if instead I put this in a for loop, because I have 10 minutes, less than 10 minutes, and if I instead did something that said button.add event listener, I have to indent that. It was just not going to work for me if I didn't. And if I did function event, I don't even care what it does, but now I've got, in a for loop, I'm going to have these functions, okay? I'm going to end up with foo, well, we'll end up with function 1, function 2, function 3, function 4, function 5, etc., okay? If nothing ever calls remove event listener, yeah, the only thing I can do at this point is remove button, because I don't even have a reference to these functions as a way to ask them to be removed. I have no way to even ask them to be removed right now, so the only thing left in the universe I can do is actually go remove that button to get rid of them. Okay?
Like one pattern I've used when it's a one-time deal is
Yep.
just give that function a name and then remove it inside the body of the listener.
Yep.
So what I was going to ask is, would you say anonymous functions have their downsides when you talk about performance, GC?
Yeah, I use them all over the place, but there are things that you don't want to use them for,
Okay.
especially things where, I mean, think about it this way. Anonymous functions are literally supposed to be short-lived things that only exist for a brief period of time. Here I'm intentionally telling it it's something that I want to live for a long period of time. So maybe don't use the thing that only is supposed to live for a short period of time if your use case is the one where you want it to live for a long period of time. That would kind of be my general rule on it. But yeah, in those cases I want something named.
Yeah, I've seen situations where even with the button, your listener is still sitting there.
Right.
So you have to systematically go through the process of getting rid of not just the down part of it, but also the listening part of it.
Right. Well, in the case of any of these engines, if the button is truly garbage collected, it'll be okay.
Oh.
Because if you remember that tree following, if it can't follow the button part of the tree, it can't follow these functions, so they'll all go together. But it would require that the button can go. If I have something out there that's holding onto the button, I am forever doomed, right? And that is why, and this is a small case, but as systems grow in size and event listeners and these sorts of things become more difficult, this gets worse and worse. The number one cause of problems is, and I'm showing it with the DOM element here because they're top level, but adding an event listener to anything that lives on window in any capacity, just no. Please don't. Because.
Don't you kind of have to?
What was that?
Don't you have to? Are you saying don't use event listeners?
I'm saying don't use event listeners that you don't remove, especially on global objects.
Sorry.
Or more specifically, either that you don't remove or can't remove. Okay? In terms of that. Or at least not ones that you expect should go away on their own. If I want to have a body unload and I know it's going to get called exactly once, okay, do whatever you want to do. All right? Because it's one. But if I'm going to do something where I'm going to build on stuff or add something, problematic. I saw somebody do this the other day in a loop inside some React stuff, and it was very well intentioned, okay? What they had decided to do was very well intentioned, as all bad code always is. Somebody was editing something, but the user could have navigated away from the page or potentially logged out. So they're like, you know what we'll do? Inside this little renderer, I will add an event listener to check to make sure they're not navigating away from the page and that they didn't click the logout button. And if they do either of those, I'm going to stop that event from happening. And that way I can stay right here and they can't navigate away from this page while they're in the middle of editing this data. Great. Worked very, very well. And every one of those renderers stayed around for the rest of time, just waiting for their moment to stop it from navigating away from that page. Just waiting. They're so excited. And none of them will ever get the chance, but they'll be in memory forever. So conceptually, yes, you have to use event listeners. Now, other languages, this is not a universal problem or solution either, but other languages, and I think eventually JavaScript will offer the ability to specify event listeners with weak reference. There's been a proposal out there in TC39, I think, for a long time, and several others. Because if you can add event listeners with weak references, then if you go back to what I had said earlier, you can literally say, well, don't keep it in memory if the only thing in the world, the only reason is because of this event listener. And that's where weak references really can come in pretty interesting with event listener stuff as well. They're very, very useful there. Okay. 5 minutes. Yeah, I get it. No, that's all good. So, all right. So to that end, let me back up a second and actually, you know what? Let me, rather than go into this next topic, because it's okay, we can always just in our time. Why don't I see if there's any questions that I can answer there specifically first within our 5 minutes, if that's okay, sir.
Yeah, it's okay. Oh, Charlie.
Oh,
Okay.
yeah. Questions?
Is there any reason why you embedded another event listener, or just to increase the number of event listener objects?
Really, I could have made 2 different buttons. I was lazy. It was just that this is the only line that was important. I just wanted to show that in one way or another that now I was building on something that was going to grow exponentially, not technically exponentially, but there was a linear growth on top of the growth that was already there. Okay. So I was trying to show that it wasn't just 2. It's now going to become, n plus 1 each time. Okay?
So Chrome aggressively garbage collects, and you said sometimes it does it so aggressively that it needs more memory. Is that one of the reasons why Chrome is so memory?
No, it's the other way, which is that it will garbage collect anytime it thinks it needs to get more memory from the operating system. Okay, so the moment that it tries to get more memory from the operating system, rather than ever make that request, the first thing it'll do is say, is there anything inside of here that I can get rid of first? So it'll always do that. Most web apps that grow like crazy are mostly because of bad code. And it is, there's this, one of the reasons I do talks like this, and one of the reasons I talk about it, is that most of the people who are writing these bigger single page apps today came from a background where they were writing small web page applications. And so they're not used to worrying about what happens inside a system over 8 hours, right? Or 9 hours of somebody using something. And all these things we're talking about today are very different. If you're gonna have a web page that you click on 3 things and fill out a form and close it, you don't have to be nearly as concerned about memory as you have to if somebody's gonna start something up in the morning and work on it throughout their whole day, because you have a very different scenario. But there's some really interesting things on memory use, and you can actually see the Chrome and Google team statistics on stuff, on what some of these websites and things use. Like when you go to Facebook, for instance, the amount of memory that it allocates when you first log into Facebook is, you would never believe it. If you turned on the profile or just went there by yourself, you will just see this thing go like this, and this, and this, because every object under the sun is created. There's just so much going on in there. But no, in general, although Chrome itself is, it uses a fair amount of memory sometimes, and actually I'll touch on that in one more second, but a lot of it does try very hard not to ask for more memory. Now, the place that it does use more is because Chrome is a just-in-time compiled virtual machine, or V8 is, which means the very first time you touch a JavaScript function, it writes code for you, like behind the scenes, so that code's going to execute very fast, but doing so requires memory. So it is actually allocating memory as well for the code it's writing that is happening behind the scenes. So depending on the quantity that it had to allocate on those first pieces, that affects it too. Okay, it's one of the other reasons I keep this example very small, because I didn't want to have to get into hey, between these 2 snapshots, lots of things changed. Well, part of that's because also that was the first time I ran that function, so that's the first time Chrome compiled it, so that's the first time these objects existed. That gets tricky in itself. Does that make some sense? Question? Oh, sorry, I didn't know if you were trying to...
I actually do have a question.
Yeah, go ahead.
So maybe this is just me not understanding garbage collectors as well, but you were saying that
Is this my chance to start over?
So you have this large tree essentially, and it's saying if I can't find a use of this, then this memory over here can be written over, right?
Yep.
But doesn't it have to keep some reference to say, this block of memory can be written over?
Well, it would actually, it's because it moves it. So it's, this is here. So what actually happens is this. Everything that it found on this side that was in use, it actually picked up and moved over here. Literally copies it. So at that point, it now knows that the useful things are all over here, so this whole thing can just be overwritten because there's nothing using it anymore.
I see.
But so that's why technically Chrome, if we keep adding, we could keep adding verbs to this thing in front of it, but it is a allocation-based, movemental, generational, ethereal garbage collector. So I got more words we can throw in there.
This will all be on YouTube. Just play it slowly through it.
Ethereal is an interesting name. Ethereal was the name of garbage collectors before generational became popular, but it's that same sort of concept. But
for complex applications, I mean, you showed the snapshot. Is it? I mean, I haven't used the snapshot to debug web applications.
Yeah.
Is it? I mean, is it easy to do that? I mean,
yeah, it's
there's
not
so
bad.
many nodes in there.
It's really not terrible. And let me try and do this real quick. I'm going really fast, I promise.
Do you promise?
I do. I'm not always good at keeping my promises. All right, this is totally stolen from like a little Hacker Noon article, but I wanted to have something that was just a little bit more like a React application. We just didn't really get to getting much into it.
Time's up.
Oh well. So in here, and this is your choosy, you know, like to do one. Is that Angular? What was it? What do you mean? This is my best work. Yeah. So, but in here, if I even do a snapshot now, you can see that while there'll be pieces in here, it's really the same pieces, and it's not crazy. If I were to debug this thing, I would look at the same things. What's my retain size versus my shallow size? Do I have any detached elements? Okay, of which I do have a few, but that's part of what React does. In fact, actually watch this. If I delete those three, as I mentioned this before, to another snapshot, look over here and ask for detached ones, I'm going to see a bunch of detached elements. But that's specifically because of the fact that React internally says, oh, I'll cache those for you in case you're going to put them back, so I'm not going to get away from them just yet. So you get used to reading what some of those things are. But yeah, it's very viable. I use these all the time in really big applications. And they work. It takes a little while to get used to them, but it's impossible without the tools. Just almost impossible. Sure that you could randomly poke at it, but it would take a really long time.
I have kind of more a comment.
Yeah.
An idiom I learned about recently was, at least on the Angular side, if you're using like RxJS a lot for your services, you can set up do a take until. So you basically take until on all your services until you're about ready to leave. So if you hook into your frameworks, like I'm leaving this form, this page, you can just set the subject to say, and I'm leaving now, and then you can clean up all your listeners in one go. So if you probably every framework has some little idiom that other people have dreamed up where you can say, or you get a callback when you're leaving the page, and you can use that to say, rip through and clean up all your.
You just gotta make sure you actually do it.
You have to actually do it.
Yeah, the good and bad things with RX specifically are that because of the subscription model where it builds on asynchronous behavior, generally you only have one place that you subscribe or unsubscribe, which means you don't really have event listeners all over the place. You usually have one to work with, which is great, because you only have one place you have to remember to undo it, ideally. The bad thing is little operators like distinct until changed, which sound like great ideas. Basically, if you think about this for a moment, they compare the last one to the next one, which is great, except for if you compare any large object, it means you will have at least two of them in memory at all times, the last one and the next one. So don't, for example, not that anyone would have done this recently, but don't take like a multi-100 megabyte file and distinct until changed anything, because it turns out there's problems there. All right, but yeah, it's actually very interesting, and it actually gets even worse if you imagine, because it is very common in some applications to model components as a type of data, meaning that then you can have components that are actually flowing through an RX composition, and those components have references and event listeners and all sorts of other things, and now you have the last one and the next one, which happen to be in memory because of a distinct until changed. So, nifty stuff. All right, so I'm gonna say this not jokingly, stick with me. This is the intro stuff. So if we want to do one sometime, if people are actually interested, we could go into the advanced one sometime and do it. And I think it could be kind of fun. But this is the stuff you kind of have to know to even to penetrate some of what's happening. All of these tools, and play with them, and they're great, and there's a lot of fun stuff in here. But all of these tools have so much more that they can give you. But it's always going to give you back information in this sort of terms that you have to be able to suss apart. And that's why I think it's most important to kind of start with understanding it from that perspective. Fair? All right, do that. Pressing the pause button.